Hi, I'm Scott Carnegie, branch manager of the Canem branch in Mississauga, Ontario. I'm going to be talking about the Noventa Toronto Western Hospital Waste-to-Energy Transfer System project. The Noventa WET system is a heating and cooling system upgrade project. The system will use thermal energy from wastewater flowing through the Toronto sewer to supply 90% of the campus heating and cooling needs, reducing the site's direct greenhouse gas emissions by about 8,400 metric tons per year. The energy supplied to the hospital from the Noventa WET system will include 1.8 billion kilowatt hours of energy over the life of the project, 19 megawatts of thermal energy capacity, over 2,400 tons of cooling capacity, and over 33 million BTUs of heating capacity. The Noventa facility will act as a district energy plant for the hospital, where the hospital will pay for energy based on the amount of kilowatts that the Noventa plant can provide to the hospital campus. This project has three distinct areas: the retrofit of the existing hospital heating and cooling system, construction of an energy transfer station utility plant, and construction of a 200-foot deep wet well for collection and screening of sewage. The new system will utilize proprietary screening equipment to separate the sewage solids from liquids. The screened sewage will be pumped to the ETS building, where it will be used to generate the hydronic heating and cooling. The new heating and cooling system will be installed over the 290,000 square foot campus, connecting 9 separate buildings in the heart of downtown Toronto. All major plant equipment will have an N+1 redundancy and enough generator capacity to island the facility to avoid the global adjustment charges, providing substantial operational cost savings. The new low temperature heating system will additionally require the replacement of the air handling unit coils across the hospital. On top of the new hydronic piping system, the project also includes the construction of a new central utilities plant with waste-to-energy heat exchangers, heat pumps, heat exchangers, and pumps. Canem was brought into the project at the 30% design phase. We work with the engineering team and general contractor to assist in the design of the new system. As this project is a retrofit in an operating hospital, we took the lead routing piping throughout the facility and mechanical spacing, making major changes to the routing plans provided by the engineers. When the project team determined the original design of the energy transfer station was not constructible, the Canem team became heavily involved in the layout and design to ensure that the piping, mechanical, and electrical equipment will be able to fit and function within this new space. One of the major project challenges arose from the design being behind schedule. The design gaps in the system required extra effort from our team to work with the project engineers. To assist with this design, Canem engaged suppliers, subcontractors, and outside BIM and design engineers for the selection of AHU coils, the structural for the rooftop and riser piping, layout and engineering of the hospital's CUP equipment, and the mechanical and electrical design for the ETS. Canem drove the project engineering teams by pressing them to keep pace with the construction requirements. Working with the hospital team also posed challenges. Since the hospital is in operation, our team was required to work around the hospital's schedule, planning any required work that would potentially impact the hospital to happen in the off hours, and requiring coordination with the hospital staff. The tight budget in this project also presented additional challenges, and value engineering became a large focus. Because of our early involvement, we were able to reduce the amount of redundant equipment and adjust the system design to remove 26 pumps and 13 heat exchangers. Additionally, we worked with the structural engineer to adjust the piping supports to more generic items that generated substantial project savings. One of the major challenges for this project was integrating the new heating system with a hospital that was designed to operate with legacy systems. As the original heating system was done with steam, converting the system to low-temperature hot water posed challenges with replacing infrastructure that was installed in the hospital during the initial build. The automation system posed a particular challenge, as our electrical team was responsible for the installation of all devices and controllers. Further to this, the new energy valves that were required for the energy-efficient operation needed to be connected to the new train automation system and integrated into the legacy Honeywell automation system. Integration of these two systems created added difficulty for the control and operation of the new equipment and required us to manage cooperation between the automation contractors and coordinate scope between these two groups. The aggressive timeline for the project construction also provided challenges, as any changes to the heating system needed to be completed before the heat was required. This allowed only a limited timeline to have the heating system retrofit work to be completed. So when structural steel components required to complete the work on the heating system were delayed just before the heating season, the team was challenged to provide a temporary heating system for the hospital until the construction could be completed. The Canem team worked with the project engineer, general contractor, project owner, and the hospital to utilize the hospital's existing system combined with the partially constructed heating system to provide heating for the hospital until the permanent system could be completed so no hospital facility or service would be impacted. This project will be the first of its kind in North America. The system will be 8 times larger than any other installation of comparable systems in Europe. Once this project is in full operation, the greenhouse gas emissions reduced will be equivalent to removing 1,811 cars from the road, 250,000 tons of carbon dioxide emissions reduced, 130 million cubic meters of natural gas, and 1.3 billion liters of cooling water will be saved.